Hello, everyone. I guess we're ready to start. So welcome to this session. We're going to discuss 3 papers today. For the first one, Niels is going to present to us. Niels is a master's student in computer science at ETH in the 3rd semester. His main interests are computer architecture, theoretical computer science, formal verification, and programming language design. He has previously been an intern at Google as a backend ML engineer, worked at the Kotlin compiler at JetBrains, and currently is actually a software engineering working student at Quanco. Moreover, he is currently in collaboration with the Safari Group, and he's designing a novel, fully general purpose and massively parallel computer architecture by exploiting the theoretical properties of interaction combinators. He's going to present for us routerless networks on chip.
Yes, thank you for the introduction. So, as you can already see, today we're going to talk about routerless network on chip. And before I actually go into the details of the paper, I will first, since it's kind of a new topic, want to give some background on how interconnects are designed in chips. So how do we actually connect the different cores in a chip? And then after we've done that, I will go into the details of the paper, what they propose, and how the results for that actually looks. So first, let us have here 16 cores and see how one might connect them up. A very simple one, a very early proposed one, technique is just a bus. Just connect every core that you have to one wire, and whenever you want to send something, you just put that signal on the wire. Obviously, you have to make sure that you don't come into conflict with the other cores, but it has some really good advantages. Actually, it's very simple, and since this simplicity, it's very efficient for a few cores. So if you just want to connect up 3 or 4 cores, a bus design is perfectly fine and will actually work very well, just because it's so simple. But obviously, there's also some downsides to this simple design. And really, the main one is that when you scale up the number of cores, obviously, you will still just have one bus, and you don't increase the throughput by just connecting more cores to it. And so you get highly limited by the bus throughput after you've connected a certain number of cores. So people came up with other topologies. One of them is the ring. Here you basically have a lot of cores, and then you have an entire ring, basically ring segments, connecting one core to the next. And then when you want to send a message, you'll just go around this ring until you hit your destination. This has some advantages compared to the simple bus. First, it's still very simple to implement, but it has a higher throughput. That is just because you don't have one single wire that limits, that's like a bottleneck for your entire communication. But also with this ring architecture, you do still have some disadvantages. And one thing is that when you increase the number of cores, obviously the ring gets longer and longer, and it actually gets longer linearly. So if you want to send a message, you have to go a lot more hops if you increase the number of cores, and so the latency scales only linearly, even though your core's distance might not scale equally. And so people came up with the so-called mesh topology, which is actually currently the most used topology, I would say. And you basically connect them in a kind of grid. And now obviously routing is not so simple. So at each of the cores, you have a simple router. And whenever you have an incoming message, you can basically choose on which of the 4 connecting segments you want to forward the message to. And this actually basically improves upon the 2 other ones by having extremely good scaling with number of cores, because you'll always find a very short path between two nodes. And so you'll keep low latency even when core count increases. And sometimes maybe you have a lot of traffic between two specific cores. And another good point about this topology is that you can actually find multiple paths from one core to the next. So if there's growing demand between two cores, you can just use multiple paths and have basically higher effective throughputs between the two. But there's some other disadvantages that come with this new kind of topology. And the biggest one is that you need these kind of routers. And this is obviously way more complicated than just passing something, for example, along a ring. And these routers, they require logic, they require buffers, and thus use area, space, and power. And you also, to make this decision, maybe you have to look into some kind of routing table. Maybe you actually have a more sophisticated routing strategy where you even look at the current demand. And so this routing decision actually takes some time. And so your packet latency increases again. And so people proposed a new topology, which is called the multi-ring. And what you do here is you basically layer a bunch of rings onto your grid, and packets just move along these rings. But since you have more rings, if you do this smartly, you can basically reduce the latencies. And you can reduce the latency a lot compared to the mesh because you don't have any routers. You don't have to make any complex decision. So packets just move along the rings once they're inserted into a ring. And if you place them smartly, you even get low hop count. Obviously, that depends on how smart you can place these rings. But there's some key disadvantages I do want to highlight. And that is, again, with scaling cores up. So this is a common theme. We want to be able to have a scalable design. And the problem is when you scale the number of cores, you can do one of two things. Either you make your loops longer, but then you run into the same issues as with the ring, where your latency just gets worse and worse because you have longer rings that your messages basically take. The other thing you can do is you can just put more rings, more smaller rings into your design that will keep the latency low, right? But then you run into the second issue, and that is that previous designs basically had to use buffer resources for all the rings that go through your node. And obviously, if you put a bunch of small rings into your design, you'll have more loops crossing your node, and thus you need a lot more resources, buffer resources. And to even be able to place these rings, the previous state-of-the-art used a genetic algorithm that basically tried out different designs that try to minimize the hop counts while still having the connectivity between all cores. But this genetic algorithm is super slow. And this brings me to what this paper wants to do. It basically wants to take the advantages of this multi-ring design or a routerless design, but be able to not be, so especially the one benefit that it really wants to have is to not have routers because of the complexity of these routers. But it basically wants to tackle the issues that previous routerless designs have. And it does that by two main things. One, it proposes a new algorithm, a recursive algorithm that lets you place these rings smartly. So you don't have to wait hours until your evolutionary algorithm finishes, and you even get better results with that. And then the second crucial step is that they introduce a technique where you can share buffer resources inside a node. And that way you can scale better, because unlike the previous technique where you needed a buffer per ring, you can share them effectively, reducing both area and power. And as you can see, the results speak for themselves. You get an extreme reduction in power and area, which is one of the main kind of results because of the sharing of the buffers. And they don't even sacrifice because they can place the ring smartly. They even have lower packet latency and increased throughput. And how they actually achieve that, this is what we're going to look into. But before they do this, the paper makes one observation that basically even stronger motivates why you want to use a multi-ring. And that is they look at current manufacturing processes of a processor. Here, the night landing kind of chip, I know they're a bit older now, but what they basically say is to connect these cores, these interconnect are usually on like a medium depth of the metal layers. You have a bunch of metal layers, in this case 13, and the medium depth one you usually use for these local interconnects. Now they take two of those the metal layer 4 and metal layer 5, and just basically do some back of the envelope calculations. Because what they see is if you take routers, the router link between each nodes, they're usually not that big, right? Maybe usually not bigger than 512 bits, oftentimes even just 256. Because if you increase the length width, you actually increase the complexity of the router even more. And so usually they're kept small. And so they calculate, even like with some conservative estimates, that you basically then, with such a 6x6 mesh router design, you only take up 3% of your available resources, of the wiring resources. And so basically what they argue is you can actually make use of, like, put more wires into that design. If you go the routerless design, you can actually handle that to be able to just route more traffic. And so given that, they see, okay, we can actually place more routers. We'll look at how they place these rings. And for that, they have a recursive algorithm. So they start with a very small grid, here 2 by 2, and then progressively you can just increase the size of the networks. And what they do is basically they say, okay, we want to use more resources, and they set themselves a so-called capping limit. They don't want to get arbitrary, obviously you don't get infinite resources. So what they say, for an n by n design, they don't want more than n wires going across. So here 2 by 2, you see there's 2 rings going in each segment. That fulfills the cap. And you see those rings go in opposite directions, so you can effectively route any packet very efficiently. Now, obviously, the question is, how do you do this for bigger designs? And so here's where the recursive algorithms come in. First, you place the design you had one step earlier, hence the recursion, in the middle of your new design. Now, you flip the direction of the loops and rotate your design by 90 degrees. Obviously, for the 2 by 2 design, that does nothing. It's still the same, but it's important for later stages. And now what about the other cores around here that we haven't connected? Well, they introduce new loops to now connect them up to all the other cores as well. So first we begin by a big loop around the outer cores. This connects up all the outer cores. And now obviously we still have to connect the outer cores to the inner cores. And we'll do that with 2 groups. First, we'll introduce loops where we connect the left-hand side. You'll see each of the loops contains the left-hand side of the cores. And then we'll have 1 loop per column in our inner column. So we connect up all the inner columns of our design. And we'll do the same with the right-hand side of our newly introduced cores. Now, this actually makes sure that every single pair of our cores are already connected. But we're in a 4 by 4 design. So what they say is we want to have at maximum 4 loops simultaneously in one segment, and we haven't reached that yet. So what they do is they introduce a new set of loops. This is not to make the connectivity. The connectivity is already assured, but it's basically to better connect them up, to ensure more loops that you can route packets through, and to also maybe have lower hop counts, because you can choose your loop however you want. All right, so how does this algorithm actually compare to, let's say, the previous evolutionary algorithm that was used? Here you can see a table of a few statistics. And first, I want you to focus on the first 2 columns. We'll see the overlapping cap, and basically what they argue is we want to get it as close as at the overlapping cap as we can to effectively use our wiring resources. And what you'll see here is that RL, the proposed algorithm, is a lot better and uses more of the wiring resources we have than IMR, the previous evolutionary algorithm. And so it makes use of the wiring resources effectively. And now if you look at the last column, you'll see the longest loop in the designs. And what you'll consistently see over all of the sizes is that the previous algorithm had longer loops, at least the longest loop was longer. And this is not good because longer loops have longer latencies. And so at least in the worst case, we know we have better latency. But what about the average case? Obviously, we are usually interested in the average case of our traffic. And what they do here is they simulate synthetic traffic between the cores, in this case, uniform traffic, and see how many hops do your packets actually have to go. And as you will see, is that RL, the proposed method, outperforms the previous evolutionary algorithm enormously, especially for bigger sizes. Though it's not as direct as the optimal mesh, which is just the Manhattan distance between the two cores. Obviously, there you can just always take the optimal path. And this is not only for the uniform distribution of traffic, this also holds for other kind of traffic patterns. And what we'll see though is that the hop count is lower, hence latency is lower. All right, now we've placed the loops, but we still have to manage the traffic somehow. And so we'll look at how we design one network interface. So one basically core that interacts with the loops. So here you'll see a zoomed in version of a network interface, and you'll see loops going through this. In this case, there's 4 loops going through the router. And here, the little boxes in the beginning are so-called single flit buffers. A flit is just, you can think of it one message. It's basically what fits on your wires. So if your wire is, I don't know, 256 bit wide, your buffer is exactly 250 bits. Now, let's see how you would inject a packet into our loops. So our core wants to send a message to someone else, here in orange, right? Obviously, not every loop is connected to every core. And so we first have to look into our routing table to see what rings actually contain the destinations we want to send it to. And maybe it happens that the first and third one actually are connected to our destination. And what we'll do now is we'll take amongst the one that are free, because you can see in the first string, it already has a packet currently going through. So this one's not free. And among the free one, we'll choose the one that has the closest distance to the destination. So in this case, the only free one is the third one. So we'll pick that, we'll inject the orange packet, and all the other packets that arrived at our network interface, we'll just pass along on their loops. All right, that's great. But unfortunately, a message or a packet in our system is not always just one single flit. Sometimes they are longer, can be 3, 5, whatever flits. And so while you're injecting such a long packet, obviously there can be incoming traffic. And so what do you do with the incoming traffic? Well, previous designs used buffers on the loops to basically buffer the incoming traffic until they're done with injecting the longer packet. And that's actually why it doesn't scale. That's just when I said in the beginning that with increasing loops going through you have to increase buffer size. So this paper proposes a new technique called extension buffers. And what they basically do is they have a shared pool of a few buffers that all of the loops can connect to. So let's see how this actually would look like in reality. You'll see now we have a longer packet of 3 flits, and we want to inject that. Again, we'll determine, okay, the third loop is the one that is currently free, and we want to inject the packet at. And so what we'll do is we will reserve one of the extension buffer for this loop and start our injection process. So we'll take our first flit of the packet, inject it into the loop, and again forward all the other traffic as we did before. But now you see there's actually new incoming traffic on the loop we're just injecting in, right? And since we're still in the process of injecting, we'll use our extension buffer that we've reserved to buffer the incoming traffic. And we'll continue buffering stuff that incoming traffic until we're done with our injection process. Now after that, obviously we have to free our extension buffer to be reused again. I would like to actually tell you how this actually works, but the paper doesn't really go into detail here. Now we've seen injection. What about ejection, right? That's actually quite straightforward. You'll just have oncoming traffic, and eventually you'll realize, oh, this package is actually meant for me. And you'll just take one of your ejection links and eject the packets out because it's meant for you. With one slight caveat, maybe you don't have, say in this case, 4 ejection links, you only have 2. What happens if there's more things currently that are all meant for you and you can't eject them all at the same time? Well, you can just eject however many you want or you can, and the rest of the ones, well, you're unlucky, you'll just send them to the next node, because it's a loop, right? Eventually it will come back to you, and then hopefully you can eject it. So this is kind of like the normal behavior of the system, but the paper actually details some quirks, some corner cases that they don't want to have, and they also propose mitigation strategies. So the first one is a live lock. As you just seen, sometimes you cannot eject a packet. So what happens if a packet just goes round and round, right? With never being able to be ejected? Well, that's not good. And so what they do is they introduce a counter on each of the packets, and they count how often does it cycle the loop. So how often did you have to actually forward it because you couldn't eject it? And then if the packet actually circles 254 times, you say, okay, this is enough. I'll reserve an ejection port for this packet. So I won't use it again until now. And I'll wait for the packet to come around. And since I've reserved it, there's nothing happening. I know that I can eject the packet through that ejection port now. So this prevents this thing. There can also arise a deadlock situation. It's a bit more subtle because on the router level, actually there cannot be any deadlock because any packet you have to forward. You cannot have it deadlocked anywhere. You will always forward it. But there can be a protocol level deadlock. What does that mean? Well, on top of your network, your controllers usually communicate via some protocol, usually with requests and reply. You might request a cache line from another core, and they will reply with the cache line. And so what can happen is that, let's say the network gets flooded with requests for you. Obviously, your controller can only take so many requests before inside the controller logic. So you have to reply to one request first to be able to accept a new one. However, in the worst case, there's so much traffic on your loops that you cannot reply. And an even worse case is if the traffic that fills the network is actually all meant for you, and you just cannot take any more requests. So this is a kind of a tricky situation, but they prevent it. How do they do it? They use the same counter they used for the lifelock prevention. And if after 255 circulations, you still basically cannot eject the packet that was meant for you, what you do is you will have a dedicated additional hardware buffer that you'll just buffer one of the packets into that's currently on your rings. What does it mean? Well, if you buffer one of them out, there's a bit of space. And in that space, you can actually put a reply to one of your cores. Well, since you've now replied to a request, you can take one more request, and you can basically put the thing you just buffered inside this additional buffer into your normal ejection queue. And this prevents this kind of deadlock. Now, the last thing that you go into is starvation. You can only inject or start injecting a packet if you actually have a free loop, right? And so theoretically, there can be constant traffic going on onto all of your loops such that you can never actually make a request. Now, this is highly unlikely, but it technically could still happen, and they want to guarantee correctness. And so what they do is they wait a really long time, because this is not the usual thing, but they just want to have this corner case to be correct. After, say, 10,000 cycles, if you still aren't able to inject a packet, what you do is you piggyback, so you basically mark one of the packets going by, and then after that packet is ejected by another interface, it sees this guinea pig message, and it will basically put a dummy. It has ejected a packet. It will put in a dummy packet that is just meant for you. So this interface X, and well, when that dummy packet actually arrived to you, you can take it out, which means there's some space in the loop, and you can actually finally make a request. All right, so how does this network actually do performance-wise? Before they measure the performance, they basically investigate, okay, we've seen we want to share the resources, right? We have a certain number of ejection ports in our interface and a certain number of extension buffers. How many of them do you actually want? And so they vary the numbers of ejection ports and extension buffers to see how this would perform. And as you can see, with one ejection port on the left, even if you vary the number of extension buffer, you don't gain much performance. But as soon as you increase the number of ejection ports to 2, you actually get a significant increase in performance, because it's just more likely that you'll be able to eject a packet. And in addition, you see right at the end here, the 16 by 16, this is actually the optimal case. So you never have to forward a packet, you can always eject it. You basically have as many resources as you want. And so as you see, even the 2.1 is very close to the optimal. And so they say, okay, this is actually the sweet spot. We use very little resources, but have almost perfect performance. So everything that follows will always have 2 ejection ports, 1 extension buffer. Now we've already seen the traffic, the synthetic traffic they put in the network. They do this again and compare against different kinds of networks. Here, mesh is just a regular mesh network. EVC is also a mesh network where you basically do some extra logic to decrease latency. And then IMR is the previous state of the art of routerless designs. And as you can see here in the red, it clearly outperforms all of the other topologies across all of the different workloads and also across all different injection rates, so all throughputs. And not only do they do this on synthetic workloads, they also introduce real benchmarks, /2, and see how the networks can handle this. And as you can see here, the small bar in red is the lowest, and lowest is better because you have low latency. And so it outperforms all of them in the 4x4 case, and you see very similar results for both the 8x8 and the 16x16 as well. Though I have to say in the 16x16, as you get bigger, you don't outperform the previous ones as big. Like there's not too much of a difference, but still outperforms. Now here's where this method actually really shines when it comes to power consumption. As you can see, there's an insane gap between RL, the proposed method, and all the previous ones. Now, how can you explain this? Well, they explain this by basically the simple design and by being able to eliminate these resources. And so you see the size of the router here, RL, is way smaller than what was previously had, and this just consumes way less energy. Now, to wrap up, I really want to get across 3 main takeaways. The first one is that the algorithm they propose effectively uses the wiring resources and can allow for low hop counts. The second one is that in comparison to a router-based design, a routerless design has the advantage of that your traffic actually travels at a 1 hop per cycle speed. So every single cycle you can forward a message, while routers have to make potentially complex decisions, which takes maybe a few cycles. And the third one, which I find really important, is that even if you only have very few buffers, you can basically have minimal resource usage, but still almost optimal performance. And so this is very good. Now, before we come to my own points on the paper, maybe first, are there any questions of the design of how they do stuff for the benchmarks before I go into the strengths and weaknesses? Please.
Thanks. So I don't know if I missed it, but could you detail like how these performance measurements, like is this a simulation, and was this also implemented in a real chip, maybe, this design?
So this is all a simulation. They use simulation techniques, and then either with synthetic or the actual workload, they basically only simulate the traffic going on the networks, and then just with the implementation logic of the system, they can see how the traffic would travel to the networks and hence also the performance of it. Yeah. So this is purely simulation based. Right.
Okay. Yeah. Okay. Yeah. Could you please go back to slide 39?
Slide 9.
39.
39. Okay. There you go.
Yeah. When you talked about deadlock prevention, you said that they basically take some packets out and store them, right? Could it be the case that you miss your chance to inject and then someone else basically fills that space?
No, because when you look at the buffer, you inject the packets that come into your single flit buffer, right? And you inject them, buffer them into a serve. So you're the first one that sits at the spot where you can inject, right? And so your injection port is right after you take the packets out. And so obviously you can make this injection without anyone else getting in there first.
Okay, thanks.
Yeah. Good questions. Okay. So let's get back to the strengths and weaknesses.
We have one more question.
Oh, one more question, yeah, sure.
You mentioned that the paper didn't go into much detail about the shared buffer, but you mentioned that in the design you forward messages if all the ejection ports are like used. Do you think it would be possible to modify the shared buffer to also buffer incoming responses that you would otherwise eject, and instead of forwarding it once more to the loop, taking it into the shared buffer and taking it out later?
Yes, I think this is possible. Maybe we can have a discussion in the end as well. This is our possible design choices. I think you'll basically what you'll see is that you actually use way more resources than you get benefit out of it. But I think this is a very good point that we can discuss later as well in the discussion. So let me first get into some strengths and weaknesses of the paper. First, I think the thing that really interests me and shocked me is the innovative technique of the extension buffer, and to actually see that you can use so minimal resources yet basically with no performance negatives. And also, I found the ring placements quite elegant, such that you don't have to wait hours for your evolutionary algorithm to finish. And another thing I really appreciated while reading the paper is that they give detailed explanation often as to why they make certain design decisions, and it helps understanding their motivation behind what they do. And as the last point, I think this is very nice to highlight as well. They really focus on the things where they think they can have the most, which can have the most results. So, for example, exactly the buffers. They identify, hey, here are some resources that we would really benefit if we could minimize them, and then they tackle exactly these kinds of problems. So that was really good. But however, the paper also has a few weaknesses that I want to highlight. First, you already mentioned it again. I think this is one of the strongest weaknesses. They don't even explain how, after you've stored something into the extension buffer, it gets strained. And not only that, I think this is non-trivial. You have to actually make some non-trivial design decisions that will impact your performance on this. And so I think this is really a weakness, and they should have detailed how this works. And the next, I said they also compared to the EVC network, but they actually never explain what it is. I had to go around, search for what it actually is. And not only did they never explain what it is, they also never mention or reference the work that actually introduced this. So I found this is also quite sloppy. Another thing that I didn't quite understand was in the beginning, they made this whole argument of, hey, we have these unused wire resources in our metal layers, right? And we should use them. And then they also say, more often, like oftentimes they say, we want to get as close to our overlapping cap to use these wire resources. But then for some reason they set their overlap, because they are themselves the ones that set this overlap cap quite arbitrarily to n for an n-base in design. And I've mentioned it before, right? If they looked at a 6x6 mesh network, it only used 3% of the resources. However, if you look at their 6x6 network, it also only uses 9% of the resources. So I don't get why they wouldn't increase this cap that they set themselves, or at least explain why they don't do so. And next, they also had some benchmark results that I was quite puzzled by. Here you see comparison. Left is the diagram I already showed you, right? It compared the performance of the networks. And here on the right, you can see the same graph. This is actually the same simulation software as well, from the original paper of IMR, so the evolutionary algorithm that placed these strings. And you can see they don't match at all. You can see IMR here performs almost up to 1 flit per node, right? While on the right, IMR only keeps up until, I don't know, 0.15, which is a huge difference. And they don't even try to explain it. And even the same with the mesh. The mesh also on the right performs about twice as good as on the left. And they don't go into detail why this is. And I think they should. Another thing that I didn't understand about their results is that if you look at IMR, right, and at the average hop count this evolutionary algorithm produces, especially for bigger designs like 16 by 16, you see it's 125. It's almost 10 times the optimal mesh. So your packets travel 10 times the difference in your network. Yet, if you look at the performance in the 16 by 16 case, you'll see that IMA still outperforms most meshes, even though that meshes are currently the most used topologies. And I find this quite puzzling that the most used topology would have somewhere a 10 times more something to compensate for this 10 times longer hop count. And as a last weakness, I want to look at these two graphs that they had side by side in their paper, and I really don't like them. First, we have no unit. Second, they managed to put 9 different shades of blue right next to each other, which makes it really hard to distinguish. And not only that, they even managed to have different bar width sizes, which makes it even harder to distinguish between the blue ones. And then if you look at the bottom graph, you'll see the 2 columns here on the right? Yellow, green, and red. They're actually duplicates of the one you already see above. And the only additional info you get in the graph below is this black one, right? And the black one is actually a 4 by 4 by 4 cube design. Now, this doesn't even have the same number of cores as an 8 by 8 grid. And so I don't even know if this is a fair comparison. And to top it off, they then say that the 3D cube design outperforms all the meshes, while you can actually see that some of the mesh designs outperform the cube design. So I think with that, there are some weaknesses that I can prove, but overall, I really like the paper. And maybe you also have some points that you'd like to discuss about this paper. Any questions, if you have some new ones, I'm welcome to answer them as well. Okay. Otherwise, I can give you some hints. We already have someone. Yeah, please.
I was just wondering if there's any kind of comparison with maybe some kind of a layout which has like a central router. Like I'm not an expert, but I was under the impression that, for instance, I think AMD's Infinity Fabric that they use on their Zen CPUs, I was under the impression that uses like a central communication component which all the cores route their traffic through. Is there any reference to that in this paper or comparison?
I think what you refer to is there's often what's called hierarchical designs. This works, for example, especially well with rings. If you don't want to have one ring that connects all of your cores, you can have basically isolated, like a few, say you divide your course into 4 portions, each of the 4 form one ring, and then you have a bigger ring that just connects the 4 things. And then you have these central hubs where one ring connects to the next hierarchy, and they don't compare this against the 2. And I have to say, the network topology in GPU specifically is even more complicated because they make other design choices there. Yeah.
All right, thank you.
All right. So you mentioned the runtime of the evolutionary algorithm that was previously used a couple of times. And why is that so meaningful? Because the way I understand it, you only have to perform this computation once for each grid size, and then you can reuse it. So this is nothing that is done like in the hardware or while running, right?
Exactly. No, you're completely right. But there's still some drawbacks. First, an evolutionary algorithm is usually not something, at least on a optimization problem this big. Usually you don't run it until completion. You run it up until a certain point, right? Mm-hmm. And the complexity gets exponentially bigger as you increase the number of cores. And so what happens, if you also saw maybe in the average hop count, that is even on a design like 16 by 16, you get such a big design core space that your evolutionary algorithm cannot even explore enough designs to have a really good one.
Okay, so with the evolutionary algorithm for certain sizes, you just cannot find a good solution.
Exactly. Yeah.
Okay. Oh, and another question immediately. Sure. So the hop count, I'm not sure how this scales exactly with the recursive algorithm, but the ring size probably scales linearly from what I've seen, right? And so the latency for a packet that cannot be ejected and is put once around the ring again also probably scales linearly. Is that desired? Because probably it shouldn't be so, right?
Yes, it's not desired because that would basically just increase latencies. But two notes. One, your loops don't increase linearly completely because there are some, if you remember the fourth group that just does loops right and left, it actually scales with the square root of n, right? Because you only have to go one width, not the entire loop. But you're right. But on a second note, this looping around actually almost never occurs. In their simulations, I think they at some point said the maximum a packet ever went around was like 3 times.
Okay, so that's probably also why you don't use the extension buffer as he proposed.
Yes.
For that. Okay.
Okay.
There are 2 questions on Zoom.
Sure.
No, I'll have it, don't worry. So, which node is responsible for the live log mitigation? Is it the source node? And then could the method be appended by having priorities in its packet?
Okay, so the first one is who does, I think it was live log, right? Live log mitigation gets each interface for themselves. So maybe I can go back. Let's see how many slides that is. Here you go. So each of the network interfaces adjusts the counter for the packets that are meant for them. And so eventually that exact interface will be the one responsible for saying, oh, wait, I couldn't eject this packet myself because it was for me. And that's why for the next round, I'll reserve an extension buffer, an ejection port, which I then can eject the packets for. So the one responsible is the one that the message is meant for. And then, sorry, the second one was about extending the design. On priorities on each packet. Okay. Potentially. So they do some, so you won't get more speed necessarily because every packet travels at one hop per second. So you can't have like an express, like route them faster. The only place where I could imagine prioritizations playing a role is in the ejection. Specifically when you eject multiple packets, you might do some prioritization. But actually, they already do some prioritization. They always pick the oldest one. So in that case, it's fair, and maybe you can have some prioritization, say, oh, even though this one packet is newer, I give it higher priority and want to eject it directly. So maybe that could be done, yeah. Maybe one thing we can still think about is, I already said that the main weakness was they don't explain how this buffer drainage works, right? And so my question to you is, could we, for example, could we implement this? Like if we had to do this buffer drainage, right? We've just put one of the incoming packets into the extension buffer because we injected a long packet. How do we drain our buffer again? Does anyone have maybe an idea how this could be done?
Well, maybe like when you're filling up the buffer, you could fill it up starting from the front, so that then once you're ready to start draining, you can just move fragments forward one slot at a time until the buffer's drained.
And what do you do with the incoming traffic? Because while you're draining your buffer, there can be more incoming traffic, right?
Yeah, that's a good point.
And that's exactly the point that I wish the paper would explain. So how could we do this? So for me, there's one thing that I immediately thought of is, hey, can we not just treat this as a new injection, right? Because we basically have a packet stored in our buffer. Why don't we just say, okay, this is now the thing we want to inject into? But we cannot use the exact same injection process we used, because when you remember, while injecting a packet, a long packet, you reserve an extension buffer, right? And so we would have to reserve like another extension buffer to inject the packet. And we actually for sure know that they don't do this, because if you remember, after determining the number of extension buffer, they only have one extension buffer. So they cannot even get a new one. And so what I came up with that might work, but still has some drawbacks, is that you basically keep the loop connected to the buffer. And then what you can do is you can start draining your buffer. And if there's incoming traffic, you'll just put that in the buffer as well. You basically have a closed loop, including your buffer. And then what you can do is you can just keep this loop open until eventually it will randomly happen that your buffer is empty, and then you can free it. Now, obviously, this has some drawback. You have to be lucky, but at least this design works. Okay, I don't know if we should end the discussion already here. I don't know how the presentations are above. Otherwise, we can also, if there's still points, or I could give you some stuff that would be fun to think about. No. I think one thing that I had some fun thinking about was that there are some inefficiencies in the ring placement algorithm, right? And why do I say that? Well, I want to focus your attention at the two cores that I marked there with the arrows. Now, what is the ring that connects the two? It's actually this loop here, right? This loop is the only one that connects the two. Now, my question is, obviously, if you scale up this design, right, you'll add more loops, like more rings around this, and also more loops in the middle of the design, right? These also include middle of the design. My question to you is, if you consider these two cores, will there ever be an additional ring that better connects the two, right? That improves the connectivity between them? Yeah, please.
So I think not, because there's they're two rows apart. So they would be connected if they were like in subsequent rows. And since they're not on the edge either, they will only always be part of the one ring that connects, like one of these B rings, I think.
Exactly. And this problem becomes increasingly worse when you go to bigger designs, right? Because say you had like a 16 by 16 core, your two cores are basically only 4 apart in Manhattan distance, yet you have to travel your entire chip's width to send one packet back and forth. And that's also obviously really inefficient. And I believe there's actually one area where you can improve this efficiency. And that's exactly the 4th group. If you remember, the first 3 group already assured connectivity between all cores. And the 4th one was just to improve the average hop count. However, if you think about it, this is extremely regular, especially if you add more of these. They always build the same pattern, right? And connect your same cores. So there is also like in your smaller designs, they also have exactly the same pattern. Obviously, you rotate them 90 degrees, but after you've rotated them 180 degrees, you're back at the same design. And so I think you can actually have more variety in your 4th group where you ensure connectivity to, for example, connect these two cores better. To not always have the same kind of, there will be a bunch of wires going left and right, for example. Could you think of other strategies of, if you don't want to take this algorithm entirely and you don't want to have a slow evolutionary algorithm, can you think of other algorithms that you might be able to optimize this problem with? Yeah.
So I still had an idea actually to modify it. So if we could add like points on the outside ring where you can sort of like change your ring once. So those would be like a little, like slightly more complicated routers, but not that much. And so then you could send them, you could change the ring you're moving on once, maybe on the edge or something like that.
Yeah, I had a similar idea. I think this can actually be very great because you'll basically sparsely place some routers across your designs. But obviously then you have to, this has some quirks, especially now, if when you decide what ring to put your packet on, maybe your destination is not even connected to the ring, and then obviously this gets complicated, but perhaps it's doable. Yeah, please.
What would happen if you give this as the result of this algorithm as a starting point to an evolutionary algorithm? Because I'm no expert on how these work, but shouldn't it only improve what you already have and find solutions like the one just proposed, like how you smartly allocate the sparse bus switching routers and everything?
Yes, I think that's a good design. If you have already very nicely scalable designs, you can just input them as far as I understood the evolution algorithm, just works perfectly fine by giving it starting points. So I think that's a good point. Yeah. You can also just treat this as a ground up optimization problem, and instead of having an evolutionary algorithm, you just have some objective function that's differentiable, and you can just use machine learning to do this. And the same group actually also investigated it, and they were basically able to subsequently find better loop placement with a machine learning approach. And basically, they model this as a reinforcement learning. Basically, the agent places loops on your design, and then you have some kind of objection function that tells you if the things are connected and if the hop counts are low. Yeah. Maybe as a last fun point, this paper came out in 2018. So quite a bit ago. And yet I wanted to look, okay, who actually mentioned this? And there's practically zero literature that mentioned this designs. There's a few that references it, say, oh, by the way, there's this fun little thing that basically eliminates routers, but no one benchmarks against them, no one discusses the results. Now, why is that? I actually, I'm not sure why this is, but it's maybe an interesting point to see if this actually has some kind of limitations that wouldn't work in real life. To be fair, these are usually ones you cannot confirm. So feel free to just have any guess. I think there's not an answer that you can actually definitely say, okay, this is the reason why. Yeah.
So maybe that is actually the case for many papers like these proposing bus designs, because I guess there's probably like millions of possible solutions that you could choose from. And in the end, large chip manufacturers probably choose only one and use it for a couple of years. And so maybe it's just not unregular that a design is not used.
Yeah, I think this is a very good point for, especially for industry. But what was, so I would have kind of expected this, but what was astounding to me that even in academic literature, it didn't pick up neither the ideas nor the design itself. And maybe there's a few points that I came up with. So we don't know if these points are actually true or not. This is just hypothesizing, right? But maybe I've already said in the weaknesses that I found some of the performance benchmark at least a bit puzzling. And so maybe the performance actually couldn't be reproduced by other groups. I mean, that's one possibility. Maybe it's actually too inflexible. Maybe people want more flexibility of how they want to basically place their cores and connect them up. And the algorithm proposed only works for very square. They give some argument why it might work for rectangular as well, but basically it only works for squares. And they also make this big argument of metal wires. I'm not an expert in metal wires, but it feels like if you have wires, you can use them for other things than just interconnects. There's probably a lot more happening inside a chip than just the protocols between say the cache controllers, right? And so I could actually see that in practice, maybe you want to use these wire resources for something else, even if you would technically have them. Or perhaps the paper here doesn't include basically optimizations you can do with routers. It's also one thing that they mention more often, that routers require expensive decision, but maybe they can be optimized that the decisions they make are actually not as expensive as you might think. So maybe this is why this is, but I would be interested in people at least talking about the results, talking if they make sense, or even publishing stuff that maybe this design has more flaws than we are presented here, but we'll see. All right, with that, I think, thank you for the nice discussion, and thank you for the attention.
No? Yeah, perfect.
So welcome to the second session of today. It's my pleasure to introduce you Johannes Gutle. He's going to discuss about this interesting paper, Bufferless NoC. Johannes is a 7th semester computer science student, and his main focus is on theoretical computer science. He's also quite excited about how we can use this knowledge in computer architecture and making better systems, essentially. So yeah, stage is yours. Thank you.
Thanks. So yeah, welcome to my talk about the paper case on bufferless routing and on-chip networks that was written by Onur Mutlu and Thomas Moskebroda and was published at the International Symposium for Computer Architecture in 2009 in Austin, Texas. Let's start with a short executive summary. So the paper identifies the problem that in on-chip networks, buffers consume a substantial amount of the system's energy, occupy space, and also add to the overall system complexity. So the goal is, or the goal of the paper is to design like a NoC that eliminates the need for those buffers in routers. And they did that by introducing BLAS, which is such a network, and also routing algorithms, that eliminate the buffers needed in routers. The evaluation shows that there's a huge energy benefit while providing similar performance when the network utilization is low. Yeah, so let's take a look at the background and take a deeper look into the problem. I mean, we've just seen talk about on-chip networks, so this is just a brief summary. I mean, on-chip networks basically connect cores, caches, accelerators, memory controllers, or other units. Each of them is connected to a router, and then those are connected by links. Design goals in NoCs are low latency and high throughput for good system performance, fairness between the cores, and also quality of service, so some kind of prioritization between the different network loads, low complexity and low cost of the system, and also very important is the energy and power consumption. Yeah, especially in high performance processes, the energy consumption is the key concern. And NoCs consume substantial portion of the system power, up to 40%. And this can basically mean like hundreds or even thousands of watts in real systems. Yeah. So before the paper, there were already several approaches, or like lots of approaches on NoCs, but all of them assume the existence of buffers in routers. And that's the case because buffers are necessary for high network throughput. If we decrease the size of buffers in existing solutions, then basically the total available bandwidth in the network also decreases. But on the other hand, there are also huge downsides, like with buffers and routers. They consume again the significant amount of the NoCs power. Like once when they're like when the buffers are read or written, and also even when they're not occupied, they use static energy. Buffers add complexity and latency to the routers. So we need logic to like read and write into the buffers. Normally, there's also some kind of credit-based flow control, and some kind of virtual channel allocation for that flow control. So routers need to communicate, for the flow control. So to see if like for the next router, for example, the buffer is not full. And buffers require a significant chip area, about 75% of NoCs total area consumption. So yeah, the question arises, can we just get rid of them? Yeah, but of course there are some concerns when going bufferless, like how much throughput do we actually lose? And how's the latency affected? Up to what injection rates can we use bufferless routing? So is it like a realistic scenario? When we get rid of those buffers, is it like are there workloads that like still work with like those low injection rates that are still like possible? So how much energy reduction can be achieved? Is it like even beneficial going bufferless? And also, are there any other benefits like in area or in complexity? Yeah. With these concerns in mind, let's look at the mechanism of BLAS. Yeah, so basically in BLAS, in lots of different NoC designs, that network packets are split up into FLITs, so smaller router units. And in our base algorithm, FLIT BLAS, each FLIT is then routed individually through the network. Yeah, so each FLIT of a packet is routed individually and then reassembled at the destination. Like in prior work, where we use buffers in the routers, when two FLITs arrive at a router in the same cycle, and both of them have like the same productive direction and the only same productive direction, and with productive direction is meant like the next router in that direction is closer to the destination of the FLIT than the current router, and then one of the FLIT gets forwarded to the ports and the other one gets buffered and like forwarded later. But when we get rid of those buffers, we obviously can't buffer like the FLITs anymore. So if there is a collision, yes, so if there's a collision, we still need to forward all incoming FLITs to some output port. Yeah, so we can see there, we basically have to reroute, packets, misroute packets, and that's called deflection. This is not new, and it's called hot potato routing in like classical network analysis. Yeah, just to elaborate a bit further on deflections. So if a packet that gets deflected, that packet has to take a longer path. This increases the latency of that FLIT. It also because it increases the latency and the longer path, it has to travel through more routers. It has to travel through more links. Like the energy the system consumes also goes up, and like in general, there are also just more. There's also more FLITs in the system, so the probability of like more collisions also goes up. Yeah, I've just said that like all incoming FLITs have to be routed to some output port. So that means that for every router, the number of input port input ports must be smaller or equal to the number of output ports, because otherwise this wouldn't be possible. And every router must be also reachable from each other router, because like if we deflect the packet or like a FLIT, then it still must be like there still must be a path to its destination somehow. But luckily, most topologies actually fulfill these requirements. Like for example, mesh topologies, torus, hypercubes, trees, etc. Yeah, when we look at the routing algorithm, let's start with the arbitration policy. So that means the policy which decides like which FLIT gets allocated to which output port in a router. Yeah, so we do this in a two-level kind of way. We first start by ranking the FLITs. The paper evaluates like several different metrics, but then uses the oldest first ranking. So basically, we just look at the age in our example. So FLIT A ranks over FLIT B here. And then in the second step, we like start with the FLIT with the highest priority and allocate it to some port. And of course, we try to allocate it to a productive output port. And then like then we continue with the ones with lower priority until like the one with the lowest priority. So there we continue with FLIT B. But since our output port facing north is already occupied, we can't use that one. So the FLIT has to get deflected here. Yeah, second part of the routing algorithm is the control flow and injection policy. So how do we inject FLITs into the system? Yeah, so we can actually just inject FLITs whenever an input port is free, because when an input port is free, then that means that also like there will be also a non-occupied like output port. Yeah, so what we do is we just insert the FLIT, and then we continue with, whoops, that was a bit fast, but we continue with the arbitration and like we continue as normal and like with the routing. So that's completely local. Yeah, that's good. Additionally, there are no deadlocks in our network, because every FLIT basically is always moving. And when we use the oldest first ranking, there are also no live locks, because eventually every FLIT will become like the oldest FLIT in the system, and then it will be directly routed on the shortest path to its destination. But there are also like potential disadvantages with routing every FLIT individually. So every FLIT needs a header, and that header needs to contain all the routing information. Then it has a negative or like a potential negative impact on package latency. So I mean, if we split the packet up into like lots of small FLITs, then the probability that one of those FLITs is deflected and has to take like a quite long path is pretty high. And there's also a potential increase in server and receiver side buffer requirements, because there's no guarantee that the FLITs will arrive in order. There's also no guarantee that they will arrive in like a certain time span or anything. Yeah, so potentially like FLITs from many different packets arrive at a receiver, and then there basically the FLITs have to be buffered until all of the other FLITs of their packets arrive. Yeah, so the authors try to find a solution for that by integrating wormhole routing into BLAS. So ideally, only the first FLIT of a packet contains the routing information, and then all the other FLITs follow that head FLIT through the system. Yeah, but then like when we look at the naive implementation of this, when like just when the head FLIT only has the routing information, all the worm is basically like the worm just follows. And then there are several problems. One is an injection problem. So basically, here we have like a green worm, a blue worm, a yellow worm, and all of them already assigned to some output port. And like this can't change because they all have to follow their head FLIT. And then when we start inserting a new worm into the system, like that worm also gets it gets assigned to an output port. But now, if a new worm arrives at an input port and suddenly all input ports get busy, then we have a problem. because we just don't have 5 output ports, and there is a collision there. Additionally, there's also a live log problem. So there's no guarantee that if a worm arrives at a router, there will be ever any productive port available, because there could be always a worm that is already assigned to that productive output port. So it could live logs could happen. So the authors changed the arbitration policy to find a solution for these problems. So first we deflect worms if necessary, the same as with flits, but then we also need to truncate worms if it's necessary. So truncating worms means that the body flit basically turns into a head flit. But that also means that we need to store the routing information inside of the router, of each worm. But since we already store the basically mapping from worms to output ports, this is not a big overhead there. And the idea is that at low congestions, worms are basically not truncated, and packets travel as worms through the system or through the network. So then additionally, we also perform arbitration not only between head flits and other head, or between 2 different head flits, but also we also can truncate a worm even if the head flit has already passed that router. And so in that case, basically the green worm is allocated to the output port facing north, and the blue one is facing to the output port west. And then now a new worm arrives, the purple one. And now when the purple worm basically has a higher ranking, it can still truncate the blue worm, and now the blue worm has to basically turn a body flit into a head flit to create a new worm, and it also it needs to truncate the worm, and potentially that worm also then is deflected. And the same is basically done when we insert packets into the system. We just truncate a worm if there's no available output port, or all the input ports get busy. Actually, you can even use that system with input buffers. So you can use that with warm blast and also with flit level blast. But the basic principle of deflection still stays the same. So we just put the flit into the input buffer when it arrives, and then it stays in that buffer until either the buffer is full, then we have to continue routing the flit. Then we must schedule that flit. Or if a productive port becomes available, then of course we also route that flit. So that means that basically the key benefit of buffers here is that we reduce the probability of misrouting, because if a deflection would happen, then there's still a chance that we can just buffer that flit. So are there any questions about the mechanism of blast until now? Yeah.
Maybe there's
There you
another.
go.
Oh, yeah.
When you say truncating a worm,
Yeah.
you have to turn a flit that's inside the body of a worm into a head flit, right? And add routing information.
Yeah.
Doesn't that mean that in the body flit, there already has to be enough space to put this routing information in, because you cannot create new space, can you?
I mean, so basically, the links still have to be big enough so that you're right. The links have to be wide enough so there fits the body plus the head.
But then I don't get why you wouldn't have the header in this body flit already from the beginning and don't have to deal with all the. So this is you can either use the entire link width to store the header, then you have the header, or you don't want to use that to store data, but then where's the space coming from to put a header?
I mean, yeah, you're right, but still like this, we basically have to route then less information. So yeah, that's still good.
So your body flits just become smaller.
And basically, yes, yeah.
Okay.
And we'll also see like the performance of OnePlus isn't that good. Like, so it's like later we'll see that the performance of OnePlus actually isn't better than FlipLess. Yeah, so that's come to the advantages and disadvantages. So like obviously there are no buffers in the routers, so we don't need any energy and also don't need any space for that. Then the control flow is purely local and like super simple. In general, the router design simplifies because there are no virtual channels, and yeah, as I said, there needs to be no communication between routers. Then the router latency also reduces. I'll talk about that in the next slide. And like when we use August 1st ranking, then there's an absence of deadlocks and also an absence of live logs. Then the system adapts quite well to congested areas. So if one node, for example, produces lots of data, or like lots of data sent from one node, then packets are just deflected away from that congested area. And additionally, if there are temporary outbursts, then the links basically function as buffers. So that's also not a big problem if like the general injection rate is low. Yeah, we'll also see there are huge area and energy savings, but yeah, I'll talk about that like more in the experimental evaluation. Yeah, now let's look at the router latency. So BLAST gets rid of input buffers and also of virtual channels. So that means, like, let's first look at the baseline router. So there we basically have a router latency of 3. Like in the first cycle, we have to do a buffer write, then route computation, then virtual channel allocation and switch allocation, then switch traversal, and then we can like send that flit out. And this can actually be improved to 2 cycles by using like speculative forwarding techniques. And for the experimental evaluation, we'll also use like a latency of 2 for our baseline routers. Then when we look at BLAST, we basically can get rid of most of those stages. We only have to do the route computation, like the arbitration, and then the switch traversal. So this means that the router latency is only 2 cycles, but we can also improve that latency to 1 cycle, and by using again like forwarding techniques. So we are sending the header information. So the routing information. We're sending the routing information 1 cycle ahead, 1 cycle ahead, like of the flit, and then the route computation can be already done. And for example, in that case, the head basically there's no real head flit anymore, or like the links contain only like the actual flit data, and then that would be an improvement basically. Yeah. So, but there are also several disadvantages. So basically, when we deflect the packet, the latency of a flit increases. In general, there's reduced available bandwidth, and there's increased increased requirements for at the receiver side. As I said, like when the buffers really arrive at the receiver out of order, or like not like close in time, then the buffer might have to be quite large. Additionally, yeah, we have this header and transmission with every flit and flip BLAST, and like still we need to have like, and even in warm BLAST we need to have like this huge overhead that we're paying for the that we're paying for the header, even if the body flits don't contain this information anymore. Yeah, let's take a look at the experimental evaluation. So they use 3 different network configurations. All of them are 2D meshes. Yeah, the first 2 use 16 nodes, and the second one is quite dense because like each node is a core and an L2 bank. And additionally, yeah, we use a network configuration with 64 nodes. Then we have 128-bit wide links, and for the base configuration for virtual channels. As benchmarks, we use like typical benchmark tests, as well as Windows desktop applications, and we use them in like homogeneous ways, and also we do heterogeneous case studies. So basically, that means that several tasks are run on the system at the same time. Yeah, and with homogeneous, we basically run just one task on the system. Additionally, we evaluate synthetic traffic patterns like uniformly random injection. Yeah, the processor the system uses is based on an Intel Pentium, and yeah, what is important that it is self-throttling. So basically, the processor stalls if there's too much contention in the network, and it realizes that. Yeah, and the system is like most of the evaluation is actually done with a perfect L2 cache. So the cache miss latency is 0 cycles, and that just puts more stress onto the system because like the injection rate is basically higher than. Yeah, so we compare 4 different versions of BLAS, like FLIT. With FLIT 2, I mean, like it is meant that we use FLIT level routing with the router latency of 2, and again, and like the same for FLIT 1, for example, router latency of 1, and worm we use wormhole routing. Yeah, so when we look at just uniformly random injection of FLITs, and we actually find that BLAS has significantly lower network saturation, so that's pretty bad. So there we can see BLAS. So basically, the latency skyrockets much earlier than with like the best baseline, and actually with like all the baselines that we evaluate. So now like the question is like such a high injection rate, like above that threshold, like a realistic scenario, or are like even all are like most of the scenarios that we evaluate basically below that threshold. And then we can see that when we like now we're looking at the build benchmark that has a moderately intensive network utilization, and with perfect caches, we can see that we have only a very little performance degradation with BLAS. That's like actually less than 4% in dense networks, and like dense networks are basically the worst case scenario because there the probability of conflicts are basically higher. Yeah, and with router latency of 1, BLAS can even outperform the baseline like in some cases, especially like if the network configuration is sparse. But then we can see that there's actually a significant energy improvement in the energy consumption of the on-chip network, and yeah, almost 40% in those cases. So there we've seen moderately intensive workloads, and then when we like the only benchmark that basically has a higher network utilization still has like not a huge performance degradation, about 10%. So now let's come to the conclusion that like those low network injection rates are actually like a really realistic scenario. So in the systems that we evaluated, especially if like the L1 miss rate is pretty low, then the injection package rate is also low, And yeah, that just means that that's actually a realistic scenario. Additionally, like real systems are self-throttling, as I've said, so that's also an advantage. So further results of the experimental evaluation are that there are actually increased receiver-side buffer requirements, but they were at most 2x, and overall the network energy still is reduced. Then when we look at the impact of memory latency, when we like operate on real caches, we have only very little slowdown, like at most 1.5%, and also like the network throughput, and like also the performance. If we use real caches, gets much better on like those high network utilization benchmarks that I've talked before. Then we look at heterogeneous application mixes. Also, like the performance degradation is like not very significant, while still having the energy savings. And there's also no significant increase in unfairness between like the different tasks. And last but not least, about 60% of the network area can be saved. So that's also quite a huge portion. So to come to a conclusion, there are lots of applications where going bufferless actually makes sense, while having huge benefits in like energy and area. So yeah, let's analyze the paper and talk about the strengths and weaknesses. So basically, it's a novel approach. It questions all the existing approaches and like their assumption that we need buffers. Then it's the first paper that, I mean, there were papers that mentioned that this maybe could work, but it's the first paper that actually like implements it and then thoroughly evaluates it. And then it not only evaluates the extreme, but also like some compromises when adding like small input buffers. So as we'll see, like at the weakness section, there are also some weaknesses, but still, it's a good foundation for further research, I think. Then, like in most of the talks we've seen in this seminar so far, like there were like quite small improvements in metrics, like at most several percent. But here we actually have like huge energy and space reduction. So yeah, that's a strength. And it's also like a kind of early evaluation of a problem use case that just gets more important over time. Like as you probably all know, like the cores inside systems just increase because the single core performance doesn't increase that much anymore. Yeah, and also in hardware accelerators, network on chips or NoCs are basically the backbone of the communication between all the different parts. And like that's also like important in machine learning, for example, in hardware accelerators for that, and also in GPUs. And yeah, then like a minor strength I'd say is also that it uses real workloads for like the evaluation, not only synthetic data. Yeah, for example, milk that we've just seen as a physics simulation. Yeah, then the paper is clearly structured and very, very understandable. Yeah, I think it was very well written. But let's look at the weaknesses. So basically, the paper is about bufferless routing, but then the receiver side buffer requirements are increased, and yeah, so the paper doesn't really explain and also doesn't really solve how the packets are reassembled. And additionally, like that's much more important, I think. So there's like it just assumes that the receiver side buffers are big enough, and there's like when they're full, basically the system fails. And so they have to be big enough for the worst case, and theoretically that kind of means like infinitely big. I mean, this won't happen like in real systems, but still, I mean, there's just no guarantee that the system will actually function. Then I've said that the complexity goes down, but actually it's quite hard to implement the routers in hardware because yeah, there's a long critical path for route computation. So first, when we do the arbitration, first we have to sort the flits. So that's already expensive. And then we have to allocate the ports in like a sequential manner. And yeah, with like when we do that, the critical path becomes so long that it's really hard and like it's really hard to implement. So that's not a bottleneck, and that like the performance has to basically go down because of this. Yeah, then in the buffered version, basically still all the incoming bits to a buffer have to be buffered. Still all the incoming flits into a router have to be buffered. So like there's not a big like dynamic energy reduction there. Yeah. So that's also a weakness, I'd say. And it also lacks some important functionality that is needed in like a real system. So some kind of starvation avoidance, like also quality of service and prioritization. Like in real network on chips, basically, or in real networks in general, we need to prioritize. We just need to be able to prioritize some packages and some flits. And also, it doesn't mention what happens, or like it explicitly mentions that that basically, if there are 40 routers and links, the system doesn't function anymore. But of course, as I've said, it's a novel approach. So I don't think that further work on this basically could then implement those functionalities. Yeah, so that's it. Do you have any questions now?
Could you go back to the evaluation where you showed the graph, the performance metrics? If I remember correctly, it was on the metrics there was the latency was one of was measured.
Where do you mean? You mean the one there?
Yes.
Yeah.
So first of all, is this the latency for a flit to arrive, for the entire package to arrive, first arrival, or is it when the package is totally received?
I know this is just the latency of like a single flits on, and in general, like the average latency of like flits from from source to destination. Yeah, that's it. Okay.
I was wondering because if a single flit takes already much longer, and we've discussed that we need a lot more flits to package the information that was required in the beginning. How much more information do we need to send? How much longer does it take in overall?
I think you're kind of right. I mean, so there's also evaluations in the paper about like package latency, etc. Yeah. So and this basically shows the same. So like the average latency basically doesn't go up that much for packets and also for flits up to a certain point, and then it's like skyrockets. So yeah, basically the average package latency and the average latency of in general network traffic shows the same behavior. Any more questions? Otherwise, we can just go to discussion. So I mean, I've just said like one of the weaknesses is that basically there's no implementation for the case that the receiver side buffer is full. So it has to be like really huge. So it has to be really huge anyways. And yeah, this could still be in real systems. It could still happen that in the worst case, basically like an error occurs. So do you have any ideas how we could like fix this problem?
Did you say there was already some kind of throttling once the network is overwhelmed? Does the buffer being full on one receiver also constitute of the network being overwhelmed?
You mean the receiver side buffer?
Yes.
I mean, kind of yes, but like that's at the basically that's at the receiver side. So we like the sender doesn't know that the network is like that the network is overwhelmed. So we would basically to inform the sender, we would then either have to send it over the already like kind of congested network, or we would have to like introduce even a new network or something. And that's so yeah.
But I thought this was the entire point of network throttling, that you basically are aware of the congestion in the network, even as the sender, and can thus throttle the messages you send.
I mean, yeah, that's kind of true, but still, I mean, in general, like it basically doesn't work. It basically doesn't. It's not like that one receiver can inform like one specific sender. But so it could be that like in general the network utilization is pretty low, but just like for one receiver, the buffer gets filled up, for example, and like all the rest of the network basically has to do nothing. So then like those throttling mechanisms aren't like clever enough to realize that.
But if we just limit all of them, since all of them realize that the network is congested at some point, it feels like, since this is a very, very unlikely situation to happen, it is quite an effective solution to the problem, no?
I mean, kind of. I'm not too sure about this, but I think that like in general, it's actually quite likely that, for example, a core requests lots of like. One core is very active and maybe all of the others are not, and then like lots of data is sent to that core and all of the others basically don't receive that much data. So I'm not sure. Like I think like of course this would have to be evaluated, but I'm not sure that like throttling the whole system just because like one receiver buffer basically gets filled up is like a really good solution. Yeah, so basically the idea that I came up with is, or like maybe not I came up with, actually following work of that. I mean, the paper was published in 2009. So in 2011, there was another paper that basically just improved the flaws of BLAST. And yeah, so basically, the receiver just drops the packet if a receiver side buffer gets full, and then it notes which package it drops. And then when space frees up in the receiver side buffer, like the receiver just notifies the sender to retransmit. Yeah, so like the first kind of idea was to just send. Like an acknowledge packet or something that the sender directly retransmits the package, but then like congestion would like even increase further. And like another idea would be to basically reserve space, send an acknowledge packet to the receiver, and then wait for an acknowledge packet at the sender, but that basically introduces a huge latency into the whole system, because then we would first have to like have the latency for the acknowledge packet, then again back to the acknowledge packet back to the sender, and then for the actual data. So, and as like latency is like super important in network on chips, this approach may work in other like computer networks, or like in general networks, but here it's not suitable. So it's actually important that we have like this realistic or this optimistic approach that the receiver just sends package or sends flits into the system. Yeah, and then like just reacts if actually if the packet actually is dropped, or like if the FLIT is actually dropped. Yeah, then I've said that going bufferless is an extreme end of a continuum. So BLAST basically suggests that we just add again input buffers to the systems, or like small input buffers to the routers. Can you think of other approaches that basically can get rid of buffers, or maybe just reduce the buffer size? I mean, okay. I mean, we've like basically a hint. Basically, we've just seen, for example, that there are also other network topologies. Can you think of other network topologies basically that reduce the need for buffers?
Yeah, I mean, we saw in the previous presentation, for example, that using rings, for example, can be a solution to reduce the buffer size. And I actually still have a question. Like, is the description as bufferless even accurate here? Because essentially we're using the network as a buffer, right? And then we're sort of recreating the same problems that we had before.
I mean, kind of like when the network utilization is high, yeah, then you're right. Basically, we're using the network as buffers, and then also the system fails. That's what we've seen. But like if the network utilization is low, then basically what we do, like basically we still use the same parts as in like the optimal parts that we would use with buffers, and then it's just basically better because yeah, then the networks don't really function as buffers. But actually, that's also kind of an approach that like to even to use the buffers even further as to use the links even further as buffers, because yeah. So because yeah, inside of the routed channels are basically also flip-flops, and they can kind of be used in a FIFO-Q kind of fashioned way. So that would also reduce the buffers at the route, like the buffer requirements, even in traditional buffered routing. Yeah. So yeah, you're right. I mean, kind of it. Yeah, like you're still kind of using the links as buffers, but that's always the case. So that's the short answer to that question. And yeah, there are also circuit switching in general might reduce the buffer size, but like setting up the connection, etc., probably is not a good approach for a network on chips because there's a huge overhead. Then you've also said, like, for example, ring topologies, and we've just seen that. Okay, then there are also approaches where you basically switch between bufferless and buffered routing for like every router, just depending on the workload it's currently facing. But of course, that also has like that means that we basically have to have the infrastructure for bufferless routing and for buffered routing. So that's also like a downside there. And then then there's also minimally buffered deflection routing. That's another like work that's basically built up on Chipper and therefore also built up on BLAS. And yeah, there the idea is that we use the deflection routing with the small side buffer. So when we add buffers to BLAS, we add input buffers. So like all the incoming flits first get buffered. But like the idea there is that when a flit would get deflected, we can just put it like inside of a side buffer, and then it gets like injected into the buffer like when there's basically an available input port. Yeah, of course, like they also have to, like you have to be basically careful that So you can't buffer every flit. if, for example, if two flits would get deflected in like the same cycle, if two flits would get deflected in the same cycle, then if we could buffer like both of those flits, then that would basically mean that in the end we would have like a buffer for every output port, kind of, and that would also like then we would also have like lots of buffer space. So yeah, there as I said, there's just like a small side buffer, just one, so we can only like buffer one flit per cycle, and yeah. So, but that's the general idea. Yeah, then like just to show you a bit like what further work has been done on BLAS. It also addresses ejection in injection bottleneck. So in 20% of all ejections, basically more than one flit could have ejected. And yeah, in like BLAS, for example, then like the flit would have to get deflected and come back to the router. And then it also improves the deflection arbitration, basically to get rid of this long critical path for like the router latency. But I won't elaborate further on this. That's like quite complex, I'd say. And yeah, so it still reduces the power a lot, and also the area compared to buffered routers, and while improving the performance like quite a bit, and closing a lot of the performance gap between like buffered and bufferless routing. So yeah, that would be it if you don't have any questions anymore. Then thanks for your attention.
Okay, I have something to say. There are a couple of issues that I want to fix. First of all, about the author list. Like the author list of this paper.
Yeah.
So you reordered them.
Sorry about that.
Yeah, I already fixed the version on the website, but also other papers that you discussed in the discussion part. You kept like the first author is not Professor Mutlu actually.
Okay.
So when you say Mutlu et al, so it's wrong essentially. One of them is actually Chris Falling.
Yeah.
So maybe it's good that you update these slides and say.
Yeah, I will. Yeah, sorry about that then.
And I also want to fix one of the question one of the answer that you give. So in general, actually, I think Q&A was not really great. Some of the answers were not really good. But for one of them, that the question was about wormhole. Basically, how we keep the information in the body just to follow the head, essentially. So that was the question, Niels, right? Yeah. So that's actually about the wormhole switching in general. We don't keep the information at body. In the router, we keep the information that's based on the input port that head enters. So header needs to enter to some of these routing. I mean, in general, actually, wormhole switching. We need to do routing algorithm, channel allocation, for example, for the head. And then we keep that information in the router in a table. And since other fleets, like the body fleets and tail, they are also following the same channel. So they are entering that router with the same link. And we use that actually metadata that we store for that link, such that they know that which channel they need to go out. So that's the way we keep information. So we don't store anything in the body, essentially. Yeah.
Then my question is, what happens if you truncate? You need to then put the header information into some body. Where does the space come from? Where do you put that?
No, we don't put that information in the body.
When you truncate?
I guess so, yeah. We can discuss also later. Yeah. But yeah, thank you. Maybe we can go with the third talk. Thank you, Johannes.
Hello. It's fine.
You think I have time to go to the bathroom?
Yeah, it's 5 minute break. You can
Try.
go.
Okay.
Hello, everyone. Welcome to the last session of this lecture. So we have Andrea today. Andrea is a master's student in electrical engineering and IT at ETH. He's in his first semester. He got his bachelor's degree from Politecnico di Milano in Italy, and he's currently interested in embedded systems, computer architecture, and parallel computing. Feel free to start.
Hello, everyone. Thank you for staying here at this time. No, it's a bit late. I'll try to keep it short. So today we're talking about this paper, which, as you can see from the title, has many elements that we've already seen today, like hierarchical rings and deflection routing. Before starting talking about the paper, I want to make a quick introduction on the topic and why we are interested in hierarchical rings. So of course, we are talking about multi-core systems, and network on chips are one of the most important topics regarding parallel computing. The idea is quite old. One of the first papers comes from 2001. The title is Route Packets, Not Wires, and it explains why it is a good choice to create a standardized network inside the chip instead of creating a specialized wire for each of the connections we want to make. And the idea is basically the same as having a city where each core is like a house, and if you want to communicate between the houses, you don't create a special road between each of them, but you make a network, which are the roads, and if you want to transmit data like post, you have a post office sending the packets to all the houses. So this, I think, it is a parallel that works, and it explains why network on chip is so popular. So to be more precise on the advantages of this technology, of course, it enables parallel communication because you can send multiple packets on the same routes. It optimizes the electrical properties because you can standardize the network, and so you can do all the optimizations of the electromagnetic properties just once and then keep it like that. It makes an efficient use of the wires that you have, because if some of the cores are idle and they're not working, then the others can still occupy the network, and this increases performance. And of course, it is a modular design, so if you want to replace one of the cores, we can do it very easily. So rings are one of the most commonly utilized types of networks on chip, and that is because they're very easy to create, to implement, but they have the big problem that they don't scale as the number of nodes increases, as we've seen previously. One possible fix, which is very simple, is to make them bidirectional. So instead of having one ring, we basically have two rings in opposite directions, and this increases the performance, of course, and it just makes the injection policy a little bit more complex. So I mentioned this because in the paper that we're going to see, it is kind of implied that all the rings are bidirectional. So keep this in mind. So if we want to scale rings even more, the best choice is to make them hierarchical, which means that we will have multiple levels of rings, and the information will go from the higher levels to the lower levels. And once it stays there, then we have all the advantages of the small rings, because they are just a bunch of smaller rings with some cores on them. So what's the disadvantage of a hierarchical network? It is that now we have a much more complex design and routing. In particular, because we don't have anymore just to take care of the interface between the local ring and the core, but also of the interface between the higher level rings and the lower level rings. And this is where we can talk about this paper and where this paper comes in the game, because, okay, I'll just show all of them. So if we want to have a chip multiprocessor, interconnects are important. The problem is that rings don't scale so much, and hierarchical rings have a very complex design. So the key idea is to try to make hierarchical rings easier by using deflection. And this will simplify the interfaces both at the local level and at the inter-ring level. And the results, which we will see later, are very compelling because we can see that because they managed to reduce the area of 50% with respect to the baseline, and the power efficiency increased a lot because the consumption went down by 20%. So let's talk about the mechanism, which is quite simple. I'll start talking about the local rings, so the interface between the local ring and the single cores, and then the other interface is just the same thing but bigger. We'll see later. So first, I want to show you the baseline that this paper uses to compare its results. It comes from a paper from 1997 to show that rings, hierarchical rings, have been used for a long time. And basically, you can see that there is a buffer, which, as we've seen in the previous presentations, are an important element because they increase performance, but they make power consumption much higher. And now we'll see that new ideas came into play. In a paper from 2009, started to think about using something different instead of the buffers. And the idea is to use multiplexers combined with registers just to have a single cycle throughput in the communication. But the key idea is that we use multiplexers instead of buffers. So we can decide using a logical circuit if a new fleet will come into the network or it will be deflected. So here the use is a mechanism where we have injection and ejection. For the injection, we still have buffers, but then to control the flow of the fleets inside the network, we will have a structure with a multiplexer and the register. For the ejection, we'll have a register and a special tool called ejector. Now, let's see how it plays out. For the injection, the input buffers are present, but they are not critical because they're not inside the critical path, which is the loop. So they don't slow down the flow of information. Then the multiplexer takes care of choosing whether the fleet will join the ring or not. And the policy is very simple. If there is already a fleet running in the ring, then we'll just keep the fleet going and we will keep the new information inside the injection buffers, which are not inside the ring. And that's it. Whereas for the ejection, we have an even more direct mechanism because when the new fleet is coming and has to go to a core, the ejector will force the new information to take a choice, either entering the core, or if the core is not ready to accept new information, it will just be dropped. And then there is a mechanism to ask to retransmit the information, which is borrowed by a previous paper, and we've mentioned it before. Basically, there is a special space reserved for that new fleet on the core, and so we will be sure that the next time it will be delivered. For the inter-ring interface, it is so we can see the baseline again that we have buffers, and we are going to remove them. Here the use is a very similar mechanism. Now we have a new tool which is a crossbar, but we can see it as just a switch. So don't be scared of this. This is just the same thing that we've seen before, but it's since now it's an inter-ring connection. We have two different rings. They are both bidirectional. So we have this time we have buffers, and they are in the critical path. So this time they couldn't remove them. But the big difference is with regards to a conventional hierarchical ring is that in a normal hierarchical ring, when a buffer is full, the flow of information in all the ring is blocked. There is a special flowing control unit which requires some more computation and takes care of that. But in this case, if the new fleet cannot enter the buffer, it is just deflected, and so we'll just make another round of the loop of the ring. And when it will find place in the buffers, it will finally be delivered. Then we have crossbars, which, as I said before, are just switches. They are used because since the rings are bidirectional, now we have to decide in which direction of the rings we prefer to send the data. Okay, so this is basically the mechanism, very simple. We can talk about the evaluation. So first of all, everything was simulated using a tool created by Safari, which is called Noculator. And this is the design that in the paper they went for. As you can see, we have three different levels. And the idea is that the higher you go with the levels, the larger the ring becomes, because it must accept more fleets. And so this is for a 64 nodes design. They also made a smaller one, which is a 16 nodes design, which is just one quadrant of this picture. And for the workloads, they chose some random benchmarks with varying communication intensity. So first notable result is that in a single thread, we have a comparable performance with the baseline. The other rectangles that you can see are a design with just a single ring, so no hierarchical ring, with different sizes. And as we can see, the performance of HIRD is basically comparable to the one of the highest ring, and it even beats the buffered hierarchical ring, which is the baseline that we are using. But the big advantage is that we have a much lower power consumption, is 26% less. And if you look at the graph with the energy efficiency, HIRD is winning against everything else. The same results apply also for a multi-thread operation. This time the performance is a little bit worse, but the power consumption is much better. And also we can see that very much like a normal hierarchical ring, latency decreases a lot when the size of the network gets bigger. Because as you can see, when we have a smaller network, the single ring is actually better than the other designs. It has a lower latency. But when the network gets bigger, then the single ring starts to show its big disadvantage, which is that it doesn't scale, as we've seen at the beginning. And HIRD starts to win. And of course, as we said from the beginning, the key idea is to make hierarchical rings simpler. And so we don't have buffers, and this reduces the area that we are using a lot. And this is one of the biggest advantages of this design. Okay, so if you have any questions about the mechanism or the evaluation, I would accept them now. Otherwise, I will start talking about the strengths and weaknesses. Okay, I think I'll go on. So, of course, I think one of the first strengths that comes up to my mind is that this design beats its baseline and all the other ring designs if we compare power consumption and performance, because we basically have the same performance at a much lower power consumption. Its design is extremely simple, as we've seen, and this comes, the beauty of it, I think, is in the fact that we are using deflection, which is commonly a very hard strategy to implement. But with rings, it is actually very easy, because if the new data cannot join the ring, then it just does another loop. Then I didn't talk about this, but there is also a safety mechanism to prevent a fleet from going forever around the loop. And I didn't talk about it because it's not written in the paper, but it comes from another paper actually. But it is present that it guarantees fairness, which I think is a good result. And because of the deflections, we are utilizing the removal of the buffers, we are utilizing the network more. We have a 90% utilization, so 90% of the network is occupied at the same time, against a 70% of the baseline, which is quite nice. But it also has some weaknesses. So if we look at the scaling of the network, when the network gets bigger, it starts to lose its advantage against the baseline. It is still better, it still has a higher energy efficiency, but not as much as when the network is just 16 nodes big. So I think this is a kind of a disadvantage, because it kind of shares the same weakness that a single ring has in this regard. Also, there are some workloads, and this is acknowledged by the paper itself, where it doesn't perform very well, and the performance actually gets much worse than a normal hierarchical ring. This is an example, the page ranking algorithm, which is the ranking, the algorithm used by Google in the past to rank web pages. Also, this is something that I found weird when I was reading the paper. As I mentioned before, there is a safety mechanism that is mentioned, but it's not talked about. And there are other circumstances where you cannot understand what's going on if you don't read the previous literature. And if you read the what I call the predecessor of this paper, which is a paper from 2014, you can actually find more or less the same ideas that are present in this paper. The pictures are the same. You don't find the same evaluations with or the graphs, but if this paper lists as the contributions things that are actually in previous papers. So I found that weird, but it's still I think it's still a great paper because it combines a lot of efforts from old papers. And also I put this weakness in quotes because it is actually a weakness of all ring networks. And I found it by looking at future literature where this paper was cited. Some researchers thought that this particular design was unappealing because it doesn't achieve as a high throughput as other networks, and this is not good for some particular applications. So yeah, we could say that the weakness of the paper is that it just focuses on beating other ring networks. It doesn't really compare itself against other kinds of networks, and I think that's a kind of a weakness. Okay. Any questions? Okay, see one.
Yeah, so I still have a question. You talked in your strengths about fairness. Do you have any information about starvation?
Sure. I'll go to the backup slide. Okay, so this is how it works. It's actually very simple. Basically, we have two different guarantee mechanisms. One is the injection mechanism, which is the one for fleets that are not, we are talking about the local interface. We have the local ring and the local cores. If a fleet is not delivered after a certain number of cycles, which for the paper is 100, then all the other injections are suspended, and so it will the buffer will clear up for sure, and then the next time the fleet will arrive, which should be quite soon because there is the retransmit mechanism, so the core will have asked to retransmit the same fleet, and the space on the buffer will be reserved. All the other injections will be blocked, and so the new fleet must be delivered. And then we have a transfer guarantee, which is for the inter-ring interface, and this is a similar idea because the buffer that we saw before, the buffer between two rings, will only accept that ring. It will so it have a reserved space for that, and it will not accept any other fleets. But I should mention that the threshold was set to 100 cycles, but actually with just 10 cycles, it was working fine. So even not a very high threshold is necessary. So that it means that there aren't many fleets that are being deflected and go around a long time. I hope that was fine. Okay. I will move on with the discussion now. Okay, so we've seen that the performance, ring's performance is not very good compared to other networks. Is there anything we can do to improve it? One of the ideas that the paper suggests is to add more bridge routers, which means that basically we have more interfaces. The one that I call the inter-ring interfaces, the paper calls them bridge routers. They're the same thing. If we add more of them, will the performance improve? Does any one of you have an idea? Otherwise, I will just give the answer. Okay, let's go. So it works, but up to a certain point. So if we go from 4 to 8, then we have a 10% increase in performance. From 8 to 16 is just plus 1.5%, which is not that great. And it doesn't really justify to double the number of routes. And that's why the paper itself uses a design with 8 bridge routers. So another thing that, okay, I gave out the answer. Okay, but anyway, it was predictable. If we make the rings wider, which is another point that the paper makes, we have an increase in performance. But as you can imagine, once the ring is wide enough, then we will never have a higher return. So once we reach a sufficient size, then we are basically done. And also, if we make the rings wider, they will consume more power, and that kind of undermines one of the big advantages of this design. So it doesn't really make sense. So this is another thing that I thought, because when I read the paper, I thought they talk a lot about deflection. So why are they dropping the fleet when it comes to the local ring, and are they not deflecting it even there? Does any of you have an answer? I have an answer. I don't know if it's correct. We'll see. Okay, so my answer is that there is something called back pressure, which means that if too many data are coming to a processor, to a core, but the core is too slow, then it won't be able to process data fast enough. So if we don't drop the fleet, but we just make it go around in the loop, then the core will just see a lot of fleets coming at it. And if it's not fast enough, then the ring will just fill up, and then we will have a live lock situation. So we cannot really deflect in the local rings because they are too small. We have to drop the fleets. Do you have any other ideas? Okay, so just one more thing, which is something the paper recommends. We can have some improvement in performance if we exploit the locality of the hierarchical ring, which is basically means that if we want to access data from a cache, let's say, we can use a cache that is very close to the local ring, because that's where hierarchical rings really shine. If the data is already in the local ring from the start, then we remove most of the data movement. And the paper, when it did its evaluations, it didn't exploit this possible advantage. If it was done, then the performance would increase. So the last point of discussion is power. So why do you think that power consumption doesn't scale well with the number of nodes? Yes, I think that's a good point.
I mean, there's also just like more overhead. Like as you add more nodes, you have to use like more bits to keep track to like address the destination for each packet. So then you have to have more complex circuitry to compare addresses. And
yeah, it makes sense, of course. What I was trying to aim at is like why this particular design doesn't scale so well. I got this answer. I don't know if it makes sense. The idea is that we are not removing buffers. Buffers are what cause a lot of power consumption, and we are not removing all of them. We are just removing the ones in the local rings. And so when we have a bigger network, we have more levels. We will still have the buffers in the inter-ring interfaces. And so the more levels you add, the more buffers you will have, and the less will be the advantage that you get from removing the buffers in the lower level, the lowest level. Okay, and yeah, last thing, what if then we make the buffers very small? That's another thing that I thought, since they consume so much power. And I'll just give you the answer because it's very simple. They already did. They made them as small as possible. But they realized that with the global to local buffer, so the inter-ring buffer, when you go from a higher level to a lower level, if you have a buffer which is too small, you will have too many deflections, and then the latency will just go up too much. With the local to global one, they made it actually the smallest possible size because it's just one fleet large. So I think that it is already optimized in that regard. Okay, this is my final slide. So if you don't have any questions, I will be done. I think it was quick.
So I have a point for one of the weaknesses you mentioned about that paper in 2014 in SpecPad.
Yes.
So actually this paper in 2016 is the extension of that paper. And it's actually quite normal to have a conference paper and then you extend it to a journal paper by providing more information, addressing more corner cases, more results. So I don't think that's actually a weakness. So yeah, I just wanted to clarify that.
Okay, yeah, sorry, I don't know. I'm not familiar on how papers are published. So as a reader, I found it a bit strange. That's all, because at least because it doesn't. Yeah, I think the real weakness is that you have to read the older paper in order to understand fully the mechanism. I think that could be a point.
Mm-hmm.
But yeah,
I'm not sure. Okay, thank you.
Okay.